Hi, everyone. Thank you so much for joining us today. My name is Julia. We are so pleased that you all could join us for, sorry, I'm at the wrong slides. That's okay. All right, we're so pleased that you all could join us today for this week's lecture in Volume 2 of our 12-week series, bringing you lectures from experts in the field covering different topics each week. This series was created by trainees and early career neuropsychologists to provide free, high-quality didactic opportunities. We would like to thank our sponsors for their financial support of the series. And before we start, here are just a few disclaimers for the series. This training is not meant to replace formal education in neuropsychology, and the views of the speakers are their own. Questions can be submitted via the Q&A box on the lower left of your screen, and a recording of today's lecture will be provided on our website later this week. Now it is my pleasure to introduce Dr. Kevin Duff for today's lecture on methods for determining cognitive change in the individual patient. Dr. Duff obtained his PhD in clinical psychology from the State University of New York in Albany in 2001. He completed his neuropsychology internship at the Southern Arizona Healthcare System in Tucson, Arizona, and his postdoctoral fellowship at the University of Oklahoma Health Sciences Center in Oklahoma City. He joined the psychiatry department at the University of Iowa in 2003, where he had clinical and research responsibilities working with patients with dementia, Huntington's disease, and a variety of other neuropsychiatric conditions. In 2009, he joined the Department of Neurology at the University of Utah as a neuropsychologist for Alzheimer's care, imaging, and research. His current research has focused primarily on the early identification of cognitive decline in neuropsychiatric illnesses, such as mild cognitive impairment, Huntington's disease, Parkinson's disease, and progressive supranuclear palsy. And the study of short-term practice effects as a unique cognitive variable in those disorders. Dr. Duff's work has been widely published in scientific journals, and he has lectured nationally and internationally on his areas of expertise. His research on mild cognitive impairment has also been funded by the National Institutes of Health since 2005. So without further ado, I will turn it over to Dr. Duff. We're so pleased to have you with us today.
Thank you very much. I appreciate it. Let me see if I can. There we go. And so thank you very much for inviting me to be a part of this lecture series. It's really great to be able to talk to 130 of you that are as interested in cognitive change as I am. Or at least I won't know that because I can really only see one or two of you at a time. There's a lot of information to cover in the next hour. So I'm probably going to just dive right into this. But for those of you who maybe accidentally showed up on this Zoom call, we're going to be focusing on methods for determining cognitive change in the individual patient. So. Just as far as disclosures, so I have, as was mentioned, I have grant funding through the NIH on a couple of different projects, and I'm also involved with a number of pharmaceutical companies, mainly on Alzheimer's disease trials. So, why is this topic important? Well, in 2011, the American Academy of Clinical Neuropsychology put out a position paper on serial neuropsychological assessment. And here were the big 6 recommendations that came from that paper. So the first 3 in green are ones that we are going to cover today. So consideration of change and repeat assessments, and that's just being aware and making sure that you're thinking about that. The second is remaining up to date on relevant research. I'm going to try to share some of that today. The third is to be familiar with pros and cons of the Reliable Change Index and the standardized regression-based change formula. So those things we'll cover. You can check those off. The last 3 are things that are sort of my charge to you all moving forward, things that the field is in desperate need of. More data on what is normal and abnormal change in people across time, how we apply these change formulas in a forensic setting, and additional guidelines on what's sort of the minimum retest interval, and how we interpret practice effects. Those things are wide open and, like I said, in need of assessment. But we'll cover these first three today. So overall, my objectives are to help you understand how we evaluate cognitive change in the individual patient or research participant. These methods apply just as much to research participants as they do patients. And the second half of my talk is really a little bit about some of the research that I've been doing using short-term cognitive change practice effects and how they tell us information about diagnosis, prognosis, brain pathology, and even treatment response in patients with mild cognitive impairment and Alzheimer's disease. So I think my talk is actually part of the clinical part of your didactic series. So I can't do a clinical talk without presenting a case. So here's our case that we will be getting back to later in the presentation. But this is a 76-year-old widowed Latina female with 10 years of education who's been complaining of increasing memory problems over the past few years. This is a fairly typical kind of case. And so I saw her 3 times over 3 different years. And if anyone knows anything about the R bands, for better or for worse, I do a lot of research on that too. So I use the R bands occasionally for research and clinical work. And so here are the different index scores on the R bands. For anybody who's not familiar, it's immediate memory, visual spatial construction, language, attention, delayed memory, and total. And all these scores, the index scores, are standard scores, so with a mean of 100 and a standard deviation of 15. And so here are this patient's scores at time 1, the very first time that I evaluated her. You can see that she definitely is having some decline, some impairment in delayed memory index, and maybe some other scores that are a little low, but remember she has 10 years of education, so we aren't necessarily expecting them to be 100 or above. When we follow her up a year later at time 2, we notice that there's some decline in immediate memory, pretty stable in visual spatial construction, little decline in language, little decline in attention, quite a bit of decline in delayed memory and in the total scale. And then when we follow her up for a 3rd time, another year later at time 3, we see much more dramatic decline across all different indexes. So when we look at these scores, sort of my question is, does she change from time 1 to time 2? And if so, on which indexes? Which of these do you think are significant changes? And then similarly, does she decline from time 2 to time 3? And again, on which indexes? And maybe overall, does she decline from time 1 to time 3? And on which indexes? And more importantly, how do we go about determining that? So I see that there was a hand raised, but let's see if I can figure out how to view that.
If the person who raised their hand wants to send their question to the Q&A box, we'll do a moderated Q&A at the end of the talk.
Oh yeah, that'd probably be great. Okay, yeah, thank you for that. Also, can you see the cursor on the screen when I move it?
Yes.
Oh, great, okay. That'll be important later. So we're gonna get back to this case later, but I just want you to think about these questions about how do we determine change and which of these scores are enough of a change that we think it is meaningful and clinically reliable, and the methods that we're gonna talk about will address this. So a little bit about change. So, I mean, there's frequent examples of looking at cognitive change within neuropsychology. For example, there's natural progression of a condition. In the work that I do, we're very interested in individuals who start with MCI and at what point do they progress to dementia. But looking at progressive multiple sclerosis or a malignant brain tumor are all conditions that we expect are going to worsen or vacillate across time. It's also important when assessing change if we're looking for recovery after an insult, and whether that insult's a traumatic brain injury or stroke or even chemotherapy, we know that people can improve over time, and so we want to track that. Similarly, we want to track if an intervention is working, whether that's a medical intervention, like some type of medication, cognitive rehabilitation, psychotherapy. All of these things potentially can improve people's cognitive functioning, yet we need to be able to identify when that meaningful change is occurring. And as I alluded to at the beginning, one of the things that came out of that position paper by AACN was in forensics cases, how do people change across time? It's really not unusual for somebody involved in a legal case to be evaluated more than once. Maybe you're working for the defense and the plaintiff's neuropsychologist has already seen this person 6 months or a year before you did, and now you're seeing them second. You need to know how to interpret that cognitive change that we expect to see. So all of these are examples of how it might play out in neuropsych. So we're going to be talking about patterns of change, and the box at the top sort of highlights the most simplistic way that we expect change to happen. So it can either stay stable, somebody can decline, or somebody can improve. But the reality is that most change probably doesn't happen so linearly or so clearly. The dashed lines at the bottom are probably a better representation of how change really happens in the real world, that people may improve, but then they may decline, or they may decline, but then improve, or improve and then plateau. These curvilinear relationships are much trickier to evaluate and to determine, but we really need to work more towards that. Most of our methods of assessing change that I'm going to talk about are in the top box, these linear relationships, but we have to start thinking more curvilinear because, again, that's probably how reality plays out. So I'm not sure if they still teach this in graduate school, but a long time ago when I went to graduate school, one of the things that we learned about scores is that in any score, for example, over here on the left, there is some large percentage of variance that's the person's true ability, and then there's also a certain percentage of variance within that score that is actually error. And so we have to know that whatever we're measuring is not always pure ability, but some error. Whenever we're looking at change, I think that error gets multiplied because there is now, again, true change within that individual, like in the circle on the right, but also error. And that error isn't just coming from the first time that we evaluate the person, but also the second time we evaluate that person, and then also some factors that happen between the time one and time two. So I think that error variance in change gets magnified even more than we see at just a single assessment. So we have to realize that even though the methods that I'll be talking about, like RCIs and SRBs, will get us a very specific number of the amount of change that we expect to see, that again, there's a lot of error probably within that that we need to account for. So what might be some of those sources of error that we see both at time one and time two and between the 2 points? Well, some of it are test variables. So for example, the reliability of the test that we're choosing. If we choose a test that has poor reliability, then that alone introduces more error into not only time one and time two, but how we evaluate change. You'll see that when we get into the change formulas, that reliability is key, one of the key variables that often ends up in predicting change. So there are some test variables. There are also some situational variables. For example, how much time passes between time one and time two, our test and our retest. In general, we know that the longer the retest interval, the poorer our assessment of change. Reliability tends to drop, and the accuracy which we predict change probably goes down. There's concepts like regression to the mean, that if you start with an extreme score, the second score is likely to come closer to the population mean, or at least the mean of that individual. So which may be very different than the population mean. But this concept that we regress towards the mean is an important thing to consider as we evaluate change. And then there's just noise factors that show up in a situation. You know, it may have been at time one, you had a regular assessment in your office and you feel like you got an accurate evaluation. At time two, maybe a fire alarm went off in your building and that interrupted the evaluation. Well, that noise only happened at one of the two visits. So that's additional error that's getting worked into that evaluation of change. And a lot of what I've focused some of my research on are individual difference variables. So what's within the individual, the person, that may alter the amount of change that we see across time. So some of the variables that we know, there's a really great meta-analysis out there, Calamia, who looked at individual difference variables on practice effects. But some of the things that came out from that paper was that age affects cognitive change, education affects cognitive change. There's an interesting set of papers by Lisa Rappaport that look at the rich get richer, and that people that start off with higher levels of education or IQ tend to benefit more from practice across time. So those factors, gender, fatigue. If somebody's tired the first time but not the second time, it may look like they're getting better when really they're not. The person's diagnosis, prior exposure to test materials like practice effects, and then even one of my colleagues here at the University of Utah, Yanasuki, does a lot of work with novelty and how a novel situation or novel tests may alter how much change we show. That the first time we experienced, for example, Wisconsin card sorting test, really challenging, but once we sort of understand the concept of it, maybe the second or the third or the fourth time we take it, and we learn that those categories change over time, it influences how much change we can actually see. So all these variables can be sources of error that alter how much change we see. Let's talk a little bit about how we do evaluate change. I mentioned before reliability, and reliability is really all we need to know, right? If we have a reliable test, then we don't have to worry as much about practice effects or we're evaluating change very accurately. I'm sure everybody's familiar, but reliability is really just the degree to which a test score is systematic and free from error. We measure it with a correlation, often a Pearson correlation in R that ranges from -1 to +1, with higher scores, whether negative or positive, indicating more reliability, that the two scores sort of track either together or opposite of one another. But in actuality, does high reliability really necessarily mean a good test? Not necessarily. All reliability really tells us is about the stability of the relative rank of the individual within the distribution. That is, they stay in the same place each time. It doesn't necessarily mean that scores are staying stable, just that that person stays either they're at the top of the distribution or the middle of the distribution or the bottom of the distribution, that they stay in the same relative spot. So here's an example that change might not always necessarily work out in a highly reliable test. So let's just look at these 4 cases. So this is time 1. Let's just assume these are all standard scores. So this first person gets 100, second person gets 101, third person gets 102, and the fourth person gets 103. Now, if we repeated these tests and there was no change, everybody got the exact same score that they did at time 1, this just means that they stayed in their same spot within the distribution. And if we actually did a correlation on these scores from time 1 to time 2 with no change, we'd get a perfect correlation, an R of 1.0. That's great, right? I mean, that's a reliable test. Now, if we see just a little bit of change for these individuals, let's assume that everybody's score goes up by 1 point from their time 1. So from 100 to 101, 101 to 102, 102 to 103, 103 to 104. Again, everybody stays in their same place within the distribution. So the correlation is, again, a perfect 1.0. And the same thing could happen if we see a big change in these people, as long as they stay in the same place in the distribution that they were at time 1. Let's say that everybody loses 15 points, okay? So they go from 100 to an 85, a 101 to an 86, and so on. Even with this massive change, everybody dropping by 15 points, but they stay in the same place in the distribution, so the correlation stays at 1.0. So again, doesn't matter if it's no change, a little change, or a big change, as long as they stay in their same spot, we get this really nice correlation. But let's look at some other variations of this. In this column here, we see a little change, but it is going to mess with the order of the distribution. This person goes from a 100 to 101. This goes from a 101 to a 100, 102 to 103, 103 to a 102. So not a lot of change, just 1 point, but their spots within the distribution gets changed. Instead of the lowest, now they're the second to the lowest. Instead of the second to the lowest, they're now the lowest, and so on. This changes the correlation from a 1 to a 0.6. Just by moving everybody 1 point, but moving their place within the distribution, we see that big change in the correlation value. And if we moved everybody by a point or two, which is still a very little change as far as a standard score, we see that we can actually drop that correlation to 0.0, showing that there's no relationship between their time 1 score and these time 2 scores, just because we move them around in the distribution. So one thing I wanted to make sure that you got is that just because we have a good correlation doesn't mean that we have a good test or that it tracks change necessarily well. That correlations of the tests are important, but it's not the only thing that we should consider. Okay, so I think as was mentioned earlier on, so one of the things I study is, and have for a long time, is practice effects. I'm actually proud to say that my first paper on practice effects when I started studying it was well back in graduate school at SUNY Albany, working with Bob McCaffrey. That was something that he was interested in, and something that I took to kind of early on. But for the most part, even when we were studying practice effects way back, and even going forward until very recently, practice effects have really largely been considered a nuisance variable. That is something that we need to control for or minimize or restrict to do away with as much as we can, because it seems to be interfering with our interpretation of follow-up scores. But as far as a definition, practice effects are improvements in cognitive test performance or scores due to repeated evaluation or exposure to the same or similar test materials. So if I give you the HVLT, here's an example at time 1, and then at some later point you get exposed to that same test, the same form of it, same words, we expect your score to improve. So here's an example from one of the early studies that I did. We were using the Hopkins Verbal Learning Test. This is the total recall. We were looking at healthy elders. We gave them, here's their baseline score since they were an intact group. At baseline, their score was at about the 58th percentile. So, that's very much what we'd expect it to be. We repeated the exact same version of the HVLT, same words, after 1 week, and their scores jumped by 20%, and now they were actually performing at the 84th percentile. Just to let you know, there was no intervention here in between. This artificial jump in performance that sometimes happens as much as 20% or more is what we call practice effects. And again, most of the field tries to cut off or remove or minimize these practice effects because they interfere with our interpretation of scores. We don't want to accidentally say that this group is now at the 84th percentile when they're probably realistically back here at the 58th. It's this artificial improvement. But we think practice effects are probably some combination of declarative memory, that is actually remembering the words that were on the HVLT, as well as procedural memory or learning the tricks of our neuropsychological tests. As you all know, many of our neuropsychological tests have sort of tricks to them, things that we don't tell people about, but sort of surprise them with later on, like that there's going to be delayed recall or that we're going to change the sorting category or what have you. But learning those by taking them a first, a second, or a third time also probably contributes to these practice effects. And again, up until now, I think most people traditionally view practice effects as a source of error, although I'll present some data later that I think that they're actually pretty valuable information. So just a couple of myths about practice effects that I'd like to dispel. One, a lot of people think that, well, as long as I have a retest interval of 6 months or more, then I don't have to worry about practice effects. We don't see practice effects over longer retest intervals. Another myth is that they're irrelevant if we have high test-retest reliability. And again, I already showed you that high test-retest reliability doesn't necessarily say a lot about change. People think that practice effects don't occur in children or older adults or in impaired patient populations. And, you know, again, since I study practice effects a lot, I try to keep up with the literature. And really, there's very limited support for any of these assumptions, any of these myths, that we do see practice effects over much longer periods of time. We see them whether the reliability is high or low. We definitely see them in children. I've seen them in older adults and in impaired populations. So don't believe any of these myths. They're really sort of out there to trick you a little bit. But I know you didn't tune just to hear me wax philosophical about practice effects and reliability and all that. You wanted to learn something. So let's get to the learning part. There's a number of different methods for assessing cognitive change, statistical methods that are widely used within the field. But I'm going to focus just on two of them in the interest of both time and the work that I've done and the work that others have done seem to indicate that these are probably the two best methods that are out there. Probably not worth really wasting our time that much with a simple discrepancy score or standard deviation index or even the original reliable change index. In a research setting, you might use a dependent t-test or repeated measures ANOVA or other fancier statistics to evaluate change. But for the individual patient, I think the reliable change index plus practice effects or the standardized regression-based change formulas are really probably the best ones. So let's learn a little bit more about these. I guess I call them the big two because, again, I think that they are the ones that are most valuable, that really serve our field the best. So let's start in the column on the left. This is the reliable change index, including practice effects. So this was developed by Gordon Clooney in 1993. So I have the unique distinction of sharing an office wall with Gordon Clooney. He works here at the University of Utah. Actually, he's semi-retired on emeritus status, but great to pick his brain whenever I get a chance to. And this RCI, including practice effects, is what we call kind of the simple difference method. And that we call it the simple difference method because we're essentially in this next line taking their time 2 score and subtracting from it their time 1 score. And then we're also subtracting from that the expected practice effects and then dividing it by the standard error of the difference. Don't worry, I'll get into all this later. For now, just sort of trust me. This is the formula for RCI plus practice effects. Now, the things that I like about the RCI plus practice effects is that it gives us a precise estimate of change. That is, this formula leads to a z-score, and that z-score can be interpreted as indicating either a lot of change, no change, or a little bit of change. And so we actually have some value that comes from that, and I'll show you how that value can be used later on. Besides having a precise estimate of change, I like the RCI plus practice effects because it accounts for practice. Obviously, that's what the plus practice effects, and also the test's reliability. So other methods of determining change might not include these variables, but this RCI plus practice effects does. It's also very widely available. You can calculate this with just about on just about every test if you have the test manual or some relevant research papers. One of the things I don't like about the RCI plus practice effect is that it's kind of a one-size-fits-all approach. That is, you're subtracting the same amount of practice effect no matter if this person does well at time 1 and time 2 or poorly at time 1 and time 2. So there's no real correction for the baseline score. And as we'll see later on, that can actually be problematic in certain cases. So it's, again, a one-size-fits-all approach that perhaps is a limitation. The SRB, or standardized regression-based change formulas, were developed by John McSweeney et al. In 1993. And interestingly, McSweeney and Clooney worked together and used a lot of the same patients as they developed either the RCI plus practice effects or the SRB. They're both co-authors on each other's papers during this. So it was really a kind of a fertile time. Cleveland Clinic, I think Dr. McSweeney was at Toledo at the time. So a lot going on in Ohio determining change. But unlike the simple difference method of the RCI, the SRB is more of what we call a predicted difference method. And the reason that's so is that we don't subtract the time one score from the time two and then take away practice effects. What we do is we predict what the person's time two score should be, this T2 prime, and then we subtract that from their actual time two score. And so we get a difference between their predicted and their actual score, and then we divide this by the standard error of the estimate. And again, I'll get all into this in just a minute, but trust me on this is what the formula is. But that's why we're predicting what their time two should be and subtracting their actual time two and seeing how much those two are different. Much like the RCI plus practice effects, this gives us a precise Z-score estimate of change. It also corrects for practice and reliability, but beyond the RCI plus practice effects, it also accounts for baseline scores and regression to the mean. And it has the potential to control for other variables that we think are important in change, like age and education and retest interval. All of those things can be worked into this regression formula to maybe more sensitively identify how much change is available. Probably one of the knocks against the SRB is that you early on had to actually have the data available to generate the regression formula. And so not everybody had access to all this data on all the tests that they would like. So these were less widely available for quite a while, but that's actually changed over time. So let's put a little sort of meat to these bones. I think it's one thing to talk about them in the abstract, but I feel like it's better to actually work through an example or two to see how they play out. So in the upcoming examples, here are some terms and numbers that I think you need to know. So going forward, T1 is their score at time one, T2 score at time two. Then we have the mean for the control group at time one and their standard deviation of the control group at time one. We have the mean of the control group at time two and the standard deviation of the control group at time two. We have the correlation between the control group's time one and time two scores. And that's represented by R12. And then here are some numbers, and these numbers I'll carry forward so you don't have to memorize them. But so we're going to pretend we have an actual patient who at time one got a score of 90. And you can say this is an IQ score or whatever you want. But at time two, they came in at a score of 80. So they dropped 10 standard score points. And then let's also assume that we have data on our control group, healthy people taking the same test across this same retest interval. At time one, their score was 100 with a standard deviation of 15. At time two, their score was 105, so they improved by about 5 points. And the standard deviation got a little bit larger at 20. And for the control group, their test-retest reliability is 0.85. So let's see how these numbers would actually work out. Again, here are all the numbers over here on the left, and the ones that are sort of, I guess, pinked out, those are the ones that we actually need for the RCI plus practice effects. So again, just to remind you, it was Clooney that developed this in 1993. There's a great paper, if you want to read it, about how they did this. But essentially, they were assessing cognitive outcomes in epilepsy patients after surgery. So they were very interested, were these surgical patients for epilepsy getting worse after surgery, or were they improving? And they were originally using, the original RCI was developed by Jacobson and Truax, but that was used for assessing changes on BDI scores in psychotherapy patients. So very different scores. And what Clooney realized was they couldn't use that original RCI. They had to correct for practice effects because cognitive scores like IQ tests or memory tests perform very differently than BDI scores or depression scores. So they adapted Jacobson and Truax's RCI to include this practice effect. Remember, here's the formula that I had on that last slide. So we take our patient's time two score and subtract out of that their time one score. And we subtract from that the mean group at time 2 minus the mean group at time 1, and we divide that by the standard error of the difference. And we're just going to shelve that standard error of the difference for a minute for a slide, but let's just plug the numbers into the top part, the numerator of our RCI formula. So remember, time 2 is just an 80, so we plug that in. Time 1 is just a 90, so we plug that in. Our mean at time 2 is 105, so we plug that in. And our mean at time 1 is 100, so we plug that in. So if we do 80 minus 90, we have minus 10. 105 minus 100 is 5. Minus 10 minus 5 is minus 15. So all of that, we get this numerator of minus 15. Now again, you're just gonna have to trust me on this one. I'll get to it in the next slide or two. But the standard error of the difference will calculate as 8.22. Again, I'll get into that, but we need our standard deviation at time 1 and reliability scores to calculate that. But next slide, we'll get to that. But if we assume that this is the correct denominator, then we take this negative 15 and divide it by the standard error of the difference, and we end up with our z-score, our RCI, corrected for practice effect z-score, of negative 1.83. And again, we can interpret this like we would any other z-score, that the amount of change that this person is showing is below expectations. It's on the negative side of the z distribution curve. So right away, we probably guess that's probably not a good thing. To know how bad that is, we'd have to compare it to a normal distribution table just to see what percentile that's at. But getting close to about the third percentile or something like that. So this is how we calculate it. It's actually very straightforward. But yeah, now, because most of you probably didn't believe me about the standard error of the difference, but what it reflects is the standard error of the difference is the spread of the distribution if we just calculated all these change scores. So the change scores is this in the control group. If we did M2 minus M1 for the whole sample in the control group, that would yield a change score of actual 0. If we average them all out for all these normal people, some people would show a lot of change, some people would show a little change, but they would average to be about 0. The standard deviation of those change scores is actually the standard error of the difference. So it's just the distribution of these change scores. That's what gets put into the denominator in our RCI plus practice effects. So how do we calculate that? Because most of the time it's not known. We don't have access to this data to know what a standard deviation of this change distribution would be. So we kind of have to estimate it. And the way that we estimate it is through the standard error of the measurement. And all that is the standard deviation at time 1 multiplied times the square root of 1 minus the correlation, the test-retest correlation. And remember, all that data was just back here. So here's our standard deviation at time 1, 15, and our test-retest of 0.85. So if we go forward, that's all I did. I just plugged that right in here. Here's that standard deviation at time 1. Multiply it times the square root. I know square roots look scary, but it's not that big of a deal. 1 minus the test-retest correlation. So it'd be 15 times 0.39, which is 1 minus 0.85, and take the square root of that, which gives us, if we did all that math, it'd be 0.58. And, oh, but that's not done. That just tells us the standard error of the measurement. I was wondering why that didn't look right. Then we plug the standard error of the measurement into this formula for the standard error of the difference, which is just the square root of 2 times that standard error of the measurement squared. Or there's a shorthand way of doing it. But if we take that 5.8, put it into our formula, square it, multiply it times 2, take the square root, that gives us the 8.2, which is, I guess there's some rounding error there. I apologize for that. My numbers really should line up. But here's this 8.22 that I used back there. So, so this formula, the standard error of the difference, is what Clooney used. But Grant Iverson, I think it was 99, he published a paper, maybe 2000, that said, hey, this standard error of the difference actually only includes the standard deviation at time 1, when really it should include both the standard deviation of the control group, both at time 1 and time 2. So Grant developed this adaptation of the formula, which most people use now, which includes both standard error of the measurement at time 1 and standard error of the measurement at time 2. And it leads to a similar but not exactly the same score, especially if, like what we see here, the standard deviation actually increases from time 1 to time 2. That's why this standard error of the difference is a little bit bigger with Dr. Iverson's formula than it is with Dr. Calooni's formula. But it still gives us the same sort of rough idea. Okay, so that is RCI. I know a little confusing at first, but if you work through that same example, just plug in the numbers in, you're going to see it's actually fairly straightforward. But I need to move a little quickly here and cover a little bit about the SRB. So again, Dr. McSweeney developed this using Gordon Clooney's sample, still the epilepsy patients. But instead of using that simple difference method, they used regression to predict what the time 2 score would be. And again, it not only accounts for practice effects and reliability, but also regression to the mean and baseline differences. Remember, here's the formula I gave you before. This is all, or actually, this is the formula I gave you before, that we take the predicted time 2 score and subtract from that, or subtract that from their actual time 2 score, and then divide that by the standard error of the estimate. How do we get this predicted time 2 score? Well, we take their time 1 score, multiply it times the beta weight from the regression formula, and then add the constant from the regression formula. The standard error of the estimate also comes from the regression formula. So you can see early on you needed the regression formula to even use this method of change, but things have improved so that 1, this data is much easier to come by, and 2, there's ways of estimating this even if you don't have the regression formula. But if you plug in the person's time 1 score, the beta weight for time 1, and the constant, you'll get a predicted time 2 score. You subtract that from their actual time 2 score and divide it by that standard error of the estimate, and that'll give you another Z-score, the RCI, for this SRB formula. But let's use an example of this. So again, here is our data for our actual participant, score of 90 at time 1, 80 at time 2. This is a paper actually I published with the R-bands a long time ago, 2004. But we published these regression-based change formulas. And I really just want to focus on the delayed memory index, the one in the red box. You'll notice inside here, there is the constant and the beta weight for the time 1 score. And there's also the standard error of the estimate. So everything that you need for calculating SRB is actually in this table from this paper. So to get our predicted time 2 score, we take the beta weight for time 1 and multiply it times that person's actual time 1 score, so that 90. So 0.71, the beta weight times the actual time 1 score is 63.9. And then we add to that this constant value that also should be available in the paper of 30.6. And when we add that to the 63.9 that we had multiplied, we get a predicted time 2 score of 94.5. So what this says is that using this data from a paper that I had published in the past, if somebody gets an actual time 1 score of 90, we expect their time 2 score to be 94.5. We expect them to increase their score because of practice effects, regression to the mean, all kinds of the test reliability. We expect them to improve their score by about 1/3 of a standard deviation. And so then we take that predicted score and subtract it from their actual score. Remember, their actual score at time 2 was an 80. So here's their 80, here's the 94.5 that we just predicted on the last slide, and here's this 11.46, which again was right here from the regression. It's the standard error of the estimate in that table. So if we plug that all in, we have negative 14.5 in our numerator, 11.46 in our denominator. We get a Z-score of negative 1.26. Again, on the negative side of our distribution table, if we had one here. And so we think that this person is changing less than normative data would suggest. So just real briefly, what is that standard error of the estimate? Well, remember I mentioned for the standard error of the difference, it was the distribution of change scores. This is the distribution of change scores on the regression line. So, you know, whenever we do a regression, it leads us a line, but we know that there's error and deviation around that line. That distribution or that error around that line is the standard error of the estimate. So that's just sort of where it comes, much more theoretical than anything that you have to really worry about. But I just wanted to let you know that it comes from that regression model. So I talked so far about these z-scores, but what z-score really is large enough to say that somebody has shown a significant change? You know, obviously negative 1.26 is less of a decline than negative 1.8 or negative 2 or negative 3. But how far down do you have to go before it's really a significant change? So just to sort of orient you, this is sort of our normal bell-shaped curve. A negative, plus or minus negative 1 z-score. A negative 1 is at the 16th percentile. A positive 1 is at the 84th percentile. Negative 2 is way down here at about the 2nd percentile. Positive z-score of 2 is about up here at the 98th percentile. In the reliable change sort of field, for a long time, we've sort of settled on using this as our cutoff for what's a reliable change. Negative plus or minus 1.645. Now, why 1.645? Well, that falls at about either below the 5th percentile or above the 95th percentile. So similar to how we kind of use P of 0.05 for research experiments as our cutoff for something statistically significant or not, in the change formula, they've sort of stuck with this. So if we see somebody whose z-score falls below negative 1.645, we say that's a reliable decline. If somebody's z-score is greater than positive 1.645, we say that that person has probably significant and reliably improved across time. Anything in between that, we'd say it'd be much more likely that that person has remained stable across time. So just real briefly, even though I said that initially these SRBs were harder to use because you needed access to the test-retest data, the regression formulas to actually use them. Masson and others in 2006 came out with a paper to show that you can actually predict or estimate these SRB values with just stuff that you might find in a test manual or most research papers. So to estimate the beta weight, all you really need is the standard deviation of some control group at time 1 and time 2. To estimate the constant, you just need the mean at time 1 and time 2 and that beta weight. And to estimate the standard error of the estimate, again, you just need standard deviations at time 1 and time 2 and the test-retest correlation. So you can actually, you actually don't need a nice table like this that gives you all the data, because you can just estimate it from you know, what we already have available. So, and the one last wrinkle of these SRBs is there are sort of two flavors of SRBs. There's the simple SRBs and the complex SRBs. So the simple SRB, which is highlighted in red, this is just an SRB that predicts a time 2 score using only the time 1 score. So that's the only thing that goes into the prediction formula. That's like the example that we just went through. But they do have what's called a complex SRB. The complex SRB not only uses the time 1 score to predict a time 2 score, but it also uses other variables. For example, in this paper, this variable here, this is a coefficient, let's see, this is D. This goes with the age of the participant. So we're using their time 1 score and their age, and then we're also using their education level. So these complex SRBs not just use the baseline score, but also some demographic variables. And you can build these regressions out so that they include lots of variables that might influence change. And I think that they lead to much more sensitive measures of change. Now, all the math that I showed you is very complex. But if you want some shortcuts, so I have a reliable change calculator. It's just a simple Excel spreadsheet. But if you ask me for it, if you send me an email, I'm more than happy to send you a copy of it. A colleague of mine from State University of New York at Albany, Brandon Gavitt, he came up with a really nice web page that does some of this work for you. This is the link to it. And then John Crawford, who is retired now, I think, but works out of the UK, also has some apps that you can use to calculate these things by just inputting in the numbers, and it does all the math for you. So if you're a little nervous about the math, here's some calculators that you can use to make sure that it's getting done right. So how might we use this in research or even in clinical practice? But so primarily it's taking the RCI or the SRB and getting that Z-score. And maybe you do that for every individual. Let's say you had a sample of 30 participants. You can, and change scores on each of them. You can calculate a Z-score for each of these individuals, and then you can either compare that to a one sample t-test of 0, because we think a 0 Z-score would indicate no change. And you can see if your group is different from that, showed more change than theoretically would, or if you had two groups, maybe you could compare the Z-score of change from one group to the Z-score of change in another group, like a control group versus an experimental group. You could see, did my experimental group change more, had a bigger Z-score than my my control group. So that's one method, is to just compare them with either one sample or t-tests or ANOVAs. Another way that I've used them is trichotomizing the scores. So we're all familiar with dichotomizing scores, of putting them into two groups. Trichotomizing is just putting them into three groups. So the way that we do this, remember we use this plus or minus negative 1.645. We can say everybody who had a Z-score of negative 1.45 or less, they go into the decline group. People that had a negative 1.645 all the way to positive 1.645, they were in the stable group. And anybody that had a score greater than positive 1.645, they were in the improved group. And then we can see we have more people in the decline group or the stable group or the improved group over time. Or again, if we have two treatment arms that we want to compare, did more people in one treatment arm decline than we would expect? So lots of different ways. And again, you can compare that with chi-square, either one sample or multiple samples. The theoretical distribution of these falling below negative 1.645 is about 5% of a normal distribution would fall in that point. About 90% of people should fall within the stable group, and 5% of the people should improve higher than positive 1.645. So you want to, you could say, compare your group to this theoretical distribution and see if more people declined or more people improved than the 5% expected that they would. But one of the things I like to do is take these Z-scores or these trichotomized groups and correlate them or regress them on other variables of interest. For example, you can see, does this Z-score of change relate to age or education or gender, or does it relate to outcome variables that are more of interest to you? I realize that we are just about out of time, so if people need to leave, I totally understand, but I'm just going to try to power through the last couple of slides if that's okay. Hearing no objections. So which of these change scores are the best? Is it the RCI plus practice effects, simple SRBs, complex SRBs? You can examine these, but I found through my work as well as the work of others that this isn't particularly helpful. All that it usually tells you is that there's oftentimes we get different Z-score values for the different scores. For example, this analysis of the HVLT, looking at change across time on the total recall score, what we see is that the simple SRB and the complex SRB, their Z-scores are similar, but they are larger than the one for the RCI plus practice effect. So they're different, but it doesn't tell you necessarily which one is better. So I don't find this particularly helpful comparing the different Z-scores. What I do find helpful is if you link the Z-score to some outcome that matters. So not a lot of people have done this, but I'm really strongly encouraging people to. So I had mentioned this before, but which of these, which change scores or which cutoffs for change scores are best linked to things like return to work or return to play or return to school? Very few people have really done studies like this. Or what Z-score is most useful in predicting who's going to worsen cognitively across time, or who's going to get better across time? What Z-score tells us who can live independently, who can drive, who can manage their own finances? What Z-score tells us who's best responding to an intervention? Or some of the work that I've done is which ones relate best to different biomarkers that we can use to enrich clinical trial samples. So again, just to highlight just a few studies that we've done. This was from a grant, one of the very first grants that I got. We were looking at practice effects in patients with mild cognitive impairment. And what we noticed was that there were two groups of patients with mild cognitive impairment. There were some that across 1 week showed a large practice effect, that they improved a lot from baseline to 1 week. And we called that group MCI plus practice effects. And then we saw another group of MCI patients that didn't show the expected practice effects. Their practice effects were much smaller than we would expect. And we actually called them MCI minus practice effects. So we had these two different groups, and when we followed them across 1 year, we noticed that those patients that showed large practice effects across 1 week, they actually remained cognitively stable across 1 year. Where those patients that showed smaller than expected practice effects, they showed a significant decline in their memory across 1 year. So what we were able to show is that we could actually predict where a patient with mild cognitive impairment was going to be 1 year from now by looking at their practice effects across 1 week. So that actually was, so we were showing that we were using the SRBs to sort of predict 1 week scores, but it was sort of showing that practice effects might be able to be used as a prognostic variable. It could tell where somebody's cognitive trajectory was going. We've also looked at practice effects as they relate to biomarkers. So in the top two pictures, these are PET amyloid scans. And the way that you read an amyloid scan is the hotter colors indicate more amyloid deposition. So this scan over here on the left, there's a lot of cooler colors. So this patient does not have a lot of amyloid in the brain. Again, amyloid is that sort of deposit that we think is linked to Alzheimer's disease. The patient over on the right shows a lot of the hotter colors. So they have a lot more amyloid throughout the brain. This person is at much greater risk for developing Alzheimer's disease. Well, we looked at the amount of practice effects that people showed over 1 week, and we dichotomized people as either showing low practice effects or high practice effects across 1 week. And then we also dichotomized their amyloid scans as either being positive, like this one on the right, or negative, like this one on the left. And so here are the numbers. We see that it's people who have low practice effects are much more likely to have a positive amyloid scan. People that have high practice effects, much more likely to have a negative amyloid scan. And actually, through the work of Gordon Clooney, he has a nice calculator for this, we could calculate an odds ratio, that the odds ratio of having a positive amyloid scan was 13.5 times higher if the person had low practice effects than if they had high practice effects. So we were actually able to use this to try to predict before somebody even had an amyloid scan if they were going to be positive or not, depending on the amount of practice effects that they show. We've looked at practice effects related to treatment response. This is just showing that the higher practice effects somebody shows relates to a better response to a cognitive intervention. And again, much like I did with the biomarkers, we saw that individuals who had high practice effects were 8.5 times more likely to respond to this cognitive intervention than patients with low practice effects. We just finished up a study, and another NIH-funded study looking at practice effects' ability to predict treatment response. And also these practice effects, so I've been using them primarily in MCI and AD, but some of the early work that I did showed that practice effects were also useful in predicting long-term cognitive trajectory in patients who are HIV positive, as well as patients with Huntington's disease. So I think that there's a lot of value for sort of using these in other patient samples as well. So just briefly, in conclusion, RCI plus practice effects and SRBs should be considered when evaluating cognitive change, both clinically and research. And I kind of underline SRB because I personally think that that's more sensitive than the RCI because it is not a one-size-fits-all. The work that I've done shows that SRBs, short-term SRBs, cognitive change across 1 week, seems like it's linked to cognitive decline or prognosis, brain pathology, and even treatment response in patients with MCI and early Alzheimer's disease. But even though the RCIs and the SRBs have been used in some clinical conditions, way more work is needed in linking them to disease progression, treatment response, and biomarkers in other cases. And just to finish up, to get back to our case, so I know you all were eagerly waiting to see what really change occurred. So remember, I'm just using the SRBs on the R bands that I showed you earlier, this 2004 paper. And for any of you that said that there was change in any of the indexes from time 1 to time 2, I would say that using SRBs would say that there's been no change. None of these change break that threshold of positive or negative 1.645. The one that comes the closest is delayed memory index. So declining from a 79 to a 71 is really only a z-score on the SRB of negative 1.37. So still within that stable range. For any of you that said there was change from time 2 to time 3, you'd be right if you said that it was for the delayed memory index. So going from a standard score of 71 to 58, that does break that cutoff. So this is the z-score, SRB z-score of negative 2.01. So that's beyond that negative 1.645. So that definitely changes. The other ones that were close was language was close right here, and total score was close, but they didn't quite break that cutoff. The real big changes happen from time 1 to time 3. That happens very large change for delayed memory index, going from a 79 to a 58 is a z-score of negative 2.5. And now language is also beyond that cutoff of negative 1.67. And the total score going from 88 to 75 is really close, negative 1.62. So with that, I will stop after an hour and 9 minutes of you people listening to me. I apologize for that. But in all fairness, the introduction was very long and probably could have been shortened. I'm just kidding. So let's see, I will stop sharing my screen so I can see if there are, so should I go to the Q&A first, Julia?
So we've been collecting the questions
on
our end.
Okay.
We do have a lot of questions that are coming in, and sure. I want to be respectful of your time. So I just want to see.
I've got lots of time. I'm still. Okay. It's only 4 o'clock here in Mountain Time, so okay. I'm still for another hour.
Perfect. We'll try to get through as many as we can. Sure. Starting with some more broad questions. The one person asked, is there any way to measure reliable change across different assessment measures? For example, a WAIS at one point, or a WISC at one point, then a WAIS at the second time point? Yeah,
that's actually a great question. I've been blessed with a lot of access to a lot of great data, and there's a paper that I did. I'll have to get the reference for it. That was looking at can we build an SRB that predicts for 2 different measures as long as they measure the same construct. So for example, comparing list learning on the R bands to total recall score on the HVLT. And so there is some data to say that we can predict from 2 measures as long as they are the same construct. Now, obviously we get a better prediction if we're going from the same measure to the same measure, but there is the possibility of predicting different measures. Yeah, there's I think it's something like predicting same versus different measures. If people are interested, you could email me and I can find the reference for it. But yeah, definitely possible.
Okay. Okay, wonderful. Thank you. Is there a time which you would use norm reference scores as opposed to raw scores?
Yeah, so that's actually a really great question. And Justin Miller, a colleague of mine who is out at the Lou Ruvo Center in Las Vegas, has actually looked at that in a paper that we did together with some data. And interestingly, what we found was that raw scores are actually more advantageous than standard scores or norm reference scores for predicting change. Now, again, I would want to validate that in other patient populations. We looked at it in our sort of older adults MCI, early AD. It's possible that better predictions would come in other patient groups where I'm thinking that, but it does seem like when we norm reference scores and standardize them, that we lose a little of the within subject variance. So I'd at least start looking with the raw scores.
Okay, that's helpful. Thank you.
Sure.
For reliable change with practice effects, the RCIPE, someone asked, can you clarify where in practice you would obtain M1 and M2?
Yeah.
The manuals provide means and standard deviations, but which one would be considered M1? And can you also get the standard error of the difference from the manuals?
Yeah, so normally you can get any of these variables from the test manual. And so, yeah, M1 would just be the first time that so normally this is in the reliability section of the manual, the part that most of us skip over. We go right to how do you administer the test, how do you interpret it. But there's a nice section on reliability and validity, and in that they often present test-retest reliability data. And so they will usually present like a mean at time 1 and a standard deviation at time 1 and a mean at time 2 and a standard deviation at time 2. And if we're really lucky, they'll report a test-retest reliability. So those are the ones that I would go with. And using that information, you can predict the whole RCI, including the standard error of the difference. The one caveat I will just say about that is that most of the information on test-retest reliability in manuals is across a much shorter period of time than we see in a standard clinical scenario. So typically the manual will present data presented across 1 week or 2 weeks or maybe even 3 weeks, when that's not a typical clinical scenario, which may be over a year or year and a half or even 2 years. So we want to just realize that that may be a slightly poorer estimate than if we could find something in a research paper that had a more appropriate retest interval.
Perfect. That was actually our next question.
Oh, great. Yeah, I can anticipate sometimes.
Next question, is there any period of time where you would expect to no longer see practice effects?
Wow. So there's actually a paper that came out several years ago, and I can dig up the reference on this. I didn't do it, but somebody found practice effects at 7 years out. So I think this was in an intact sample, and I think so this starts to intersect with variables that probably affect practice effects. So age and retest interval and condition of interest. So the more intact the person, and also probably cognitive domain, something I didn't really mention that much about. We see larger practice effects on tests like memory tests or tests that have unique solutions to them. We see them less on tests that are more sort of crystallized abilities like vocabulary or reading ability. So it may vary a lot, but again, some people have found them out as far as 7 years.
Wow, that's a long time.
It is a long time.
Let's see, next question has to do with estimating the values for the standardized regression-based change formula, which you discussed. If you're not wanting to not estimate them, do you know of any measures that have published regression values, or are there particular types of papers or keywords that you would use to find those beta weights?
Yeah, actually, that's a great question. So I would actually recommend, so wherever you do your searching, whether it's PubMed or PsycInfo or something like that, yeah, look for, in quotations, standardized regression based. That's the sort of what SRB is sort of abbreviated for. And that's much more likely to yield anything. Again, like that 2004 paper, and there was a follow-up one that we did in 2005 for the R bands. And I've published some on HVLT, BVMTR, trails, simple digit modalities, tests that we frequently use. But there's definitely a lack of them for things like the WACE, especially the newer versions of WACE and WIMS, Newer versions of tests are slower to come out. But if that's part of your regular clinical battery and you do repeat testing on people, there's big need to try to pull that data together and publish it.
Okay, this is a good question. So this person says, thank you for a very informative lecture. Their question is, to calculate z-scores using either of the methods, do you need to compare to a control sample for M1 and M2 with exactly the same test-retest interval as your patients?
Right. So yeah, typically we never find any data that exactly matches our participant. It's usually getting as close as you can, and sometimes we have to make sacrifices. We may find an age group that matches our participant or patient, but the retest interval is longer or shorter, and we have to decide which of those variables are most important. Again, I often find I have to make sacrifices. So find what you can that's the best that you can, and try to consider that the z-score that you get, that there's some error built into that, and realize that maybe using a strict cutoff of that negative 1.645 maybe isn't the best. Maybe be a little more flexible with that, especially if you've had to make sacrifices.
Gotcha, that certainly makes sense. This person asks, are there any issues for tests for reliable change for tests where score distributions depart from normality? For example, trail making test or ceiling effects in the Boston naming test?
Yeah, so that's a fantastic question. And actually, so remember, one of the things I had sort of warned people about is that most of these change formulas only are really designed to look at linear change, and that curvilinear change is important. But they're also largely designed to look at normally distributed scores, and many, as all of us know, a lot of our cognitive scores, test scores, are not normally distributed. And that's one of the reasons why we have focused much more on like total recall and even delayed recall as opposed to recognition scores. Recognition scores on memory tests are notoriously skewed. And so you'd think that it would be an argument for using those standard scores or norm reference scores. But again, at least the work that Justin and I did seemed to suggest that the raw scores are still probably best. But I think that there's a need to look at that. What happens if we have really skewed scores versus normally distributed scores? That's a research paper right there of something that I don't think anybody's really investigated.
Okay, well, thank you so much, Dr. Duff. I know we have a lot of questions here.
So if one of my slides had my email address on it, but I've already been getting some emails from people, but it's kevin.duff@HSC, and that's for Health Sciences Center, .utah.edu. If anybody wants to email me questions, sadly, reliable change is one of the things I like talking about the most. So I'm happy to reply and also send you any of the calculators or stuff that I talked about. But thank you so much to Know Neuropsychology for sponsoring this. Again, I think this is a really important topic, and I appreciate that so many people turned out late in the day on the East Coast anyway and hung around. So thanks again for the opportunity to present.
Yeah, thank you so much. I'm so sorry we have to cut it short. Maybe we'll have to do a part two.
All right, well, take care.
Thank you.
Have a good day.